So electrochemistry is this nice blend up of the chemical phenomena that we're used to thinking about intuitively. So thinking about free energy changes or enthalpy or entropy changes and how those relate to the spontaneity of a reaction and thinking about things on the molecular scale. But the external drivers of electrochemical systems are often thought about from a physical perspective, which makes them a little bit more tangible, but also a little bit less intuitive in the vernacular that we're used to describing chemical systems. So what I like to do, and I'm not the only one, is to relate some of the metrics used to describe electrochemical systems, things like voltage, current, charge, and resistance, to something that you might have a little bit more intuition about, and that's hydraulic systems. And by hydraulic, I mean water flowing in a pipe. And so thinking about water flowing in a pipe, like when you open the tap to wash your hands, or open the tap to take a shower, etc. Turns out that the metrics we use to describe electrons flowing in a circuit, in a wire, are exactly analogous to thinking about water as it flows through a pipe. And by exactly, I mean exactly, such that the solution to the differential equations of the Maxwell equations, which produce the Ohm's law, which I have written down here in green, that's the change in voltage, or just voltage, is equal to current times resistance. There's an exact analogy in the hydraulic systems where the difference in pressure in a pipe, which drives fluid flow, is equal to flow rate of that water times its resistance. And so I often like to teach through that analogy, at least to first initially develop the intuition around electrical metrics and how they might be used in electrochemistry. So blending the two. And so I have a picture, I just grabbed this off the internet, which relates those two different types of phenomenon. So you have the circuit in the top right, and then you have sort of the equivalent water analogy. So I'll walk you through both. So in the circuit analogy, we have our power source, which is also the source of electrons, and that's the battery in this case. And then we have the wire, which is the conduit by which the electrons are guided, so they can only pass through there. And then we have some impediment to flow of those electrons, which we call resistance in that circuit. And then we have the current, which is marked by I, which is the flow rate, literally. It's how fast or how many of those electrons are passing a certain point in a given time. And so we have, so voltage here is analogous to, in a water system, it's analogous to the pressure or the difference in pressure in a pipe. If you think about a pipe like the one we have here, if you have no pressure difference on a pipe, if you've got, let's just say you've got a long pipe here and there's water, it's filled up with water, and the pressure on this side is exactly the same as the pressure on this side, this system is in equilibrium, right? Intuitively, this makes sense to you, right? Because there's no difference in pressure, so there's no driving force for this liquid to flow one way or another. But if you crank up the pressure at the inlet here, and you keep the pressure small at the exit, which is naturally true, just simply because whatever the pressure is at the exit is typically just going to be the atmospheric pressure. So if we crank up the pressure above atmospheric pressure here, using a pump or using something else, then we have a net flow of water. It's exactly the same in an electrical system. What drives electrons to flow is a net difference in what we call, and what actually historically was called, electron pressure. We've since renamed that as voltage, but you can think about voltage as electron pressure. It simply states that on a battery, one side of the battery is at a higher pressure than the other side. And typically, if you go on to learn circuits, or you go on to take my Chem 342 class, you'll learn a lot about circuits. And you'll learn that usually on this end, on what we call the low side of the battery, this is at ground, so you'll see a little symbol like this, which is this equivalent of saying 0 volts. And so if this side of the battery is at, say, 3 volts, then the voltage difference between this side and the other side is 3 volts. That's just like saying the pressure difference in a pipe is 100 psi. That's the driving force for electrons. Electrons themselves then are equivalent to the water. The measure of sort of the volume of water passing through would be volume in the hydraulic system, and in an electrical system we consider that charge, and we measure that in the SI unit of coulombs. But we'll show you shortly that coulombs are directly related to moles of electrons through this thing called Faraday's constant, or F. And so you can think about charge, even though it feels abstract, it's literally a metric for how many electrons are flowing through. And then of course we have the corollary between current, which is the flow rate in water, and those two are directly analogous. And so in the water scenario, one way to develop pressure would just be have a huge tank of water, right? That's the equivalent of having a pump to create the pressure. And this is how, city water tanks work. So often you'll see these giant tanks on the city's horizon that look, like this, and then they'll say, welcome to whatever my town is, and maybe there'll be a clever slogan here. And so the way that these things work are exactly like this, where you have city water that gets pumped up into this, stored up inside of this volume here, and now you've got gravity working essentially as your pressure differential. Now the pressure in here, or the gravity, the mass times gravity here, which generates the force or the pressure per unit area, allows this to then generate pressure in your homes. And so this thing flows off, goes into your house, and then it gets to your kitchen tap or your shower, and say this is your shower head here. You open up the tap and water flows out. Why? Because at the end of the pipe here in your house, that pressure is simply 1 atmosphere, or even lower than that if you're in Colorado Springs, compared with what it is here. But we have to consider, just like an electrical system, there is resistance to the flow of that water from the point A, in this case, the water tower, and point B, the home tap for you to use. And that's the resistance in an electrical circuit can be thought of simply as just a constriction or a reduction in the diameter of a pipe as the water's flowing through it. And it makes intuitive sense to you, right? If you have a pipe that looks like this in scenario 1, there's really not much impediment to the water flow between the pressure drop from high to low. But if we have another pipe here, and then all of a sudden we force that water through a much smaller constriction, and say maybe this is a really old pipe in your house, right? This is maybe the pipe that leads up to your house, the mains that's maintained by the city, but then when it gets into your house, it's filled up with 80 years of gunk. And so the actual active diameter is much smaller. The pressure drop is still the same, but now much of that pressure, as you can imagine, is lost here. And so much of what we'd consider, if you had high pressure here and you had low pressure here, much of the pressure, whatever this intrinsic pressure, is going to be lost simply by trying to force all your water in through here. And so much of this original pressure is lost here, and so you end up having less pressure on the end compared to if you just had a non-constricted pipe. The same is exactly true in an electrical phenomenon, where here we have a resistor instead of a constriction, but you could think about it exactly the same. It is a constriction. A resistor is simply, typically it's a ceramic block that's often made up of sand, and that just slows down the amount of electrons that can pass through it, and so much of the voltage, much of the original energy is lost simply to getting the electrons through that resistor. So those are the two analogies. I like to think about these because they're identical, literally identical in these two systems. We often, I should say, we often call the difference in voltage across an element like a resistor. So like in this resistor, we would measure the resistance by measuring here and here, and what we would measure is essentially the electron pressure on the high side and the electron pressure on the low side, and that would tell us how much of the original voltage was lost to this resistor. And we often call that a voltage drop, just like in plumber's vernacular, they would call this phenomenon a pressure drop, because you've taken a high pressure and you've dropped most of that high pressure across a constriction. This is why, if you clean out your pipes, you can end up getting a much higher pressure at your head, simply because less of that original pressure or energy in the water is lost to that constriction. Exact same analogy in an electrical sense. And so this is really helpful framing for you to at least for me. I like this sort of framing, so you can often think about when we're talking about things like current in a circuit or in an electrochemical cell, what we're really referring to is the flow rate. And that analogy is totally sound. When we're talking about the voltage, what we're really talking about is the electrical pressure, the electron pressure in the system. We're talking about charge in coulombs. What we're really talking about is the volume of electrons being pushed through the system. And when we talk about resistance, these two things are, believe it or not, they're measured even in the same thing. So they're the same. They're really the constriction or restriction to flow in the system. So I mentioned that a bridge between the physical system or the physical description of things, as we mentioned before, things like voltage, current, charge, and the chemical system, things that are occurring on the molecular scale, occurs through the relation to this thing called the Faraday's constant. So charge, which is a physical phenomenon, but it relates certainly stoichiometrically to a redox reaction or electrochemical reaction. That's measured in coulombs, and we mark that as C. That's the SI unit for charge. And charge often will be written as Q. Sometimes people use lowercase q or uppercase Q. Don't be confused. Don't be confused with Q. Q is overused. It's often used as heat as well if you're used to thinking about thermodynamics. But charge is noted in Q here, measured in coulombs, and we use Faraday's constant to convert between the two. And so the conversion between coulombs and moles of electrons are that there are 96,485 coulombs per 1 mole of electrons. So this is our conversion between the physical world and physical descriptions of the world and the chemical world and molecular descriptions of that system. So we'll use this often. It is sort of our Rosetta Stone in being able to communicate between the two, because we will measure physically the number of coulombs passed, and we'll use something like a multimeter or a potentiometer or a potentiostat, where we've got some instrument display and we'll allow current to flow through the system. If this is a battery, and we'll measure this just like I showed in the sort of intro video to chapter 14. So we'll measure this as current, and you can imagine then we'll end up with something where we have current in terms of I measured in amps, which is coulombs per second, as a function of time in seconds or minutes or whatever that is. So you end up having current and you measure that as a function of time. Well, if we want to extract, well, how much, how do we think about this in terms of how the chemical system has changed? Well, we need to think about that in terms of moles of electrons, right? Because typically we'll have a reaction, maybe that's iron 3 plus an electron mix iron 2 plus, right? We're thinking in terms of electrons here in that redox reaction. So we need to think about in terms of moles of electrons, but we're not measuring moles of electrons. We're measuring actually current, which is a time-based measure of charge. And so what we would need to do in this circumstance, if this measurement were conducted, because current is literally coulombs per second, then what we'll do is integrate the current system or the current function with respect to time, and that's the same as taking the area under this curve, and what we get is Q, which is charge, right? So if we integrate this whole curve that we measure, all the current as a function of time, we get charge. So we'll get, maybe we passed 15 coulombs in that duration of time, and we want to think, well, what does that mean in terms of our chemical system? Well, we take 15 coulombs here and we divide by 96485, that gives us the moles of electrons, and then we can stoichiometrically relate those moles of electrons to our chemical reaction as long as we have a balanced redox reaction. That's how we're relating physical measurements or physical metrics of electrochemistry to chemical or molecular processes that are occurring at sort of the redox level. Okay, so current, I think, is a pretty intuitive measure. The SI unit is the amp or the ampere, which is also equal to 1 coulomb per second. And I just talked to you about how we might extract then coulombs, use Faraday's constant to get to sort of moles of electrons and relate that to a stoichiometric equivalent in a chemical reaction. Voltage is more of this nebulous idea, and in the hydraulic analogy we related that to a change in pressure. But how do we relate that, fundamentally? That's a little bit harder. So I'll give you just a quick intro flavor for what this might be, but the rest of this I'll save for if you go on to study electrochemistry. This is sort of the day one intro for a graduate level electrochemistry course, but it's important because, at least for me, it's helpful to understand how these things like voltage are actually related to a chemical system. And so if you've taken a physical chemistry course, some of you may have already had that, you may have been exposed to this notion of chemical potential energy, which is this mu character here, mu sub I just being some generic ith species here. So normally, and what you have learned so far, is the chemical potential energy it's really the capacity for a chemical system to do work, really in terms of releasing energy or gaining energy. And so it's a direct molar proxy for Gibbs free energy. So that's our closest relation to something we might know. And so up to this point, you've considered chemical potential energy, and implicit in that definition of chemical potential energy of a system, we look at the difference in the molar chemical potential energy of species, and that tells us whether or not a system is going to go downhill or uphill. And we measured that at least macroscopically for a system as the change in free energy. That's what you might have learned in a thermodynamics course, or at least a precursor to in like a Chem 108 course. But it fits with our intuition. So chemical potential energy is no mystery. It's something you've already sort of ingrained into your intuition as understanding as a chemist. But when we talk about electrochemical systems, we introduce this sort of more nuanced definition where we have this thing called electrochemical potential energy. And it introduces this second term here. And the second term, which we do not consider when we're thinking purely about delta G and the molar Gibbs free energy change, or the chemical potential energy change of the system, is that for charged species, there's an added energy component or potential energy component of the system that interacts with electrostatic potentials. And so the second term, it might feel intuitive to you. You have whatever the charge of that charged species is, if it's an ion. You then have the Faraday constant, which converts us from physical space to chemical space. And then you have whatever the electrostatic potential is of the environment. So if that ion is sitting in a 1 volt per meter electrostatic field, then it's going to interact, and it's going to have implicit potential energy that's different than simply the chemical potential energy of a non-charged species. That's what this whole extra term is, and the electrochemical potential energy then is the direct proxy, or it's really, I should say, the voltage is a direct measure or proxy of the difference in electrochemical potential energy of a system. So normally we're talking about energy in terms of joules, which is a direct proxy for the change in chemical potential energy. But once you have charged species in an electrostatic field, now we're invoking an electrochemical component, which just adds that extra term. So really, it's not that different than what you've thought of, but I'm trying to relate it back to fundamental components of either purely chemical potential energy or electrochemical potential energy. One gets measured in just the simple energy units we're used to, one gets measured in voltage as sort of the macroscopic metric there. And just for your own sort of intuition, 1 volt in terms of units is the same as 1 joule per 1 coulomb. And so what that really means is the energy required to move 1 coulomb of charge in a particular space. And so it's sort of a work definition here because it's energy per unit, in this case unit of a charge species, which is why we get this extra term that's added on here. I'm not going to evaluate you on this. This is purely for your own help in understanding what electrochemistry is and what something like a voltage measurement actually is as it relates to fundamental chemical species. From a macroscopic sense, what all of this means here, or how that manifests if we're thinking about bulk changes, macroscopic changes, it simplifies into this expression. So that means that the change in free energy of a system is then related to the minus NFE here, N being the charge per unit, the absolute charge per unit, or the number of moles is another way to think about that, number of moles in a stoichiometric reaction. So if you've got something like iron 3 plus an electron proceeds to iron 2 plus, in this case it's the number of moles in a stoichiometric conversion. So this N would be just 1 in this case. F is Faraday's constant. And then E here is a little misleading, and I don't like the fact that it's written as just E, because really what's implied by E is a change in E. And so when we're converting a change in free energy, what we're really evaluating here, if we're computing an E here, is a difference in voltage. So delta E is being voltage. So this would be a change in voltage for a system. Or, in other words, we could go back the other way. A difference in voltage in a chemical system can equate to a difference in free energy change for a system. So this is always being computed with respect to two half reactions. You can't really have just an absolute value of E. It doesn't mean anything. It's always measured with respect to something else. Just like there's no use in having just a Gibbs free energy for something. We're always relating it to a standard reference. So that's why we always have a difference in free energy. That's what makes it useful over the course of a reaction. So don't be confused here. This is really a difference in voltage. But this is the sort of macroscopic descriptor.